Welcome to online lecture 6, where we're going to focus here in the first part to Earth and its coordinate system. So why do we even have one? Why do we have a coordinate system? Well, it's crucial to be able to define location on Earth's surface. And this, of course, might be review for some of you, but we'll just kind of flesh out how can we identify location on Earth's surface. First off, we need to have some known points, some known locations. So we have here is the axis of rotation. So this is the vertical. This is essentially what the Earth is rotating on. And so this is a vertical line. And so where it essentially penetrates the surface, where it essentially leaves, would say, the surface, where it overlaps, where we have this cross between the surface and the axis, that's our North Pole. Down here, of course, where the axis of rotation intersects with the surface on the southern tip of the Earth, that's the South Pole. So there we go. We have two known points, two known locations. Even further, if I do perpendicular from that axis of rotation, we find the equator, which is represented here as this red line. And so that shows the furthest extent. So we have this curvature over here, this curvature over here. The furthest extent of that curve is noted here by the equator. So where it essentially bulges the most, let's say. So now what we can do is we can say, okay, we can now identify locations by whether or not they're north of that red line. And then we can give a distance from that red line. So as we go farther away, we essentially have number or a definition of a location. It is so far away from the red line. Similarly, we can go down here to the southern hemisphere and do that there. And so essentially what we have here is we have all locations between our North Pole and our equator and our South Pole can now be identified, can now be defined. So here we have that axis of rotation and our perpendicular red line being our good friend, the equator, which is at 0 degrees. And so what I did was I said to the PowerPoint, hey, PowerPoint, can you take that 0 degree line and rotate it 23.5 degrees? And that then forms these two different lines of latitude. And so now all points along this particular green line is 23.5 degrees north, and all locations along this green line down here are 23.5 degrees south. All that was is just me asking this line here and rotating it 23.5 degrees. Further, let's do it again. Let's do it now for 66.6 degrees. And so now I said take that 0 degree, rotate it 66.6. Now all points along this line are 66.6 degrees south, also known as the Antarctic Circle. And up here, 66.6 degrees north, the Arctic Circle. Finally, I said PowerPoint, let's rotate that sucker 40 degrees. And then that helps us then identify Indianapolis's location here at 40 degrees north. So what I just did is I just laid down on top of our Earth parallel lines, which we call, of course, latitude lines, and they go from 0 to 90. Those are positive numbers, and so 0 to 90 positive, where here we have 0 to 90, and these are representatives of negative number. And so beforehand, this would be negative 66.6, and this would be positive 66.6, as a way to differentiate between northern and southern. But we can also do this with longitude. And so longitude are vertical lines, also known as meridians. And so what they do is they have an origin at one of the poles and a destination at the other pole. And so all lines of latitude, all meridians, essentially they begin at a pole and end at another pole. Even further, this here is not the prime meridian. The prime meridian's over on top of Africa and Europe. But that's the 0 line for these lines of longitude. And from there, you can go 180 one way or 180 the other way. And when you get to the other side, where that line, where those 180s essentially overlap, that's the 180th meridian, and that's also known as the international date line. We refer to numbers as being negative 180 as you go from the prime meridian west, so the Americas would then be a negative longitude value, whereas if you would go to the east of the prime meridian towards much of Europe, to much of Asia, Australia, then you would have a positive longitude number. These lines here of lines of latitude and longitude represent a grid on our map. Those could also be referred to as a graticule, Graticule. And we'll notice that these are in 30-degree increments, and so what that means is 30 degrees of latitude or longitude separates each line. And you'll note as I zoom in, the graticule changes to 15 degrees. And eventually we go to 10 degrees, 5, and eventually we'll get to the 1-degree Graticule Grid. And you'll note just on the northeast side of the metropolitan Indianapolis area, we have two important lines that cross. We have the 86 degrees west longitude and the 40-degree north line of latitude. Knowing that, then this intersection here will be where the 40-degree north line of latitude intersects with the 87 degrees west line of longitude. And of course, we can go even further. So we have, in case of their GIS or cartography, we're going to see these types of systems used. First off, it's called a sexagesimal system, and that's the DMS, or the degrees, minutes, and seconds. And it's not really a decimal system per se. Yes, it does include decimal values for precision, but here we have the degree, then we have the minutes, then we have the seconds. And so essentially this is divided up as far as time. And so it's essentially, this is 46 minutes. So think of this as being 46 over 60, and then this is 26.112 over 60, as there's 60 seconds in a minute. Notice the positive latitude means that this is in the northern hemisphere, and the negative longitude means this is in the western hemisphere. Even further, you'll see locations that use decimal degrees to denote and define a location. This is going to be a little bit more precise. And so here's the same example. I took those particular values here and just converted them to decimal degrees. And so now 39.77392, comma, negative 86.176.276. This is, I believe, the exact location of the IUPUI Campus Center. And a theme that we've come across throughout these videos is if we can convert things to numbers, locations, colors, text, if we can convert them to numbers, we can then start doing things with them. In this case, we're going to start using them to show locations as precisely as possible. We represent these always with the latitude first, the longitude second. So what you'll have is you'll have either a north or south suffix for latitude. So at the very end, you'll put either north or south, or a positive negative prefix. And once again, I've explained positive in terms of latitude, northern hemisphere is positive, southern hemisphere is negative. And in terms of longitude, the east and the west, the positive is east and the negative is west. And of course, to complicate things in even further, the Earth is actually an ellipsoid. It's not a sphere or a spheroid. The ellipsoid is in this case, the yellow shape, and the spheroid is the magenta shape. Technically, well, to be precise, the Earth is what we call an oblate spheroid, but we're just thinking of it as an ellipse. And so what that means is we'll have to then think about location not on a perfect round ball, but on an irregular shaped kind of oval ellipse in which it's been flattened at the poles and kind of bulging out on the sides. But the actual true figure and shape of Earth, it's not a perfect ellipse. It's something what we'll call or reference as a geoid. And what this is the shape of Earth that's based on what we call global mean sea level. And so we might have the undulations from Mount Everest to Mariana Trench and the topography that you see on Earth's surface, but the true shape of Earth, it's sort of lumpy, has a lumpy shape that all relates to the gravitational pull, which is assumed that it's the same for all places. However, because of the gooey inside of Earth, combined with the materials that make up the surface, combined with mountainous areas, continental areas, the gravitational pull on Earth's surface varies from place to place. Thus, the Earth, it's not a perfect ellipse. This is what makes it challenging to do mathematical calculations and, in general, just identify precise locations along Earth's surface. Wouldn't this be a whole lot less complex if this was not the case? So not only do we have Earth represented as an ellipse, not a sphere, that ellipse, it's undulating, it's lumpy, it's not perfect. So we need to account for this shape when we're trying to identify locations on Earth's surface. Okay, this here is an exaggeration of the geoid, just trying to make a point here. So if I try to add a reference ellipsoid that tries to kind of essentially be the average geoid, which I do here, it's good, it's useful, but you'll notice we have areas here where the ellipse is below the surface, and then areas here where the ellipse are above the surface. But like I said, this ellipsoid, it's easier to place the coordinate system grid on it than the geoid. Try to do a cross-section view here. This shows the surface area. So here is land, and of course we have water. And the purple is the geoid, which represents the global mean sea level. And then the ellipsoid here is the yellow line. And so why this all starts to matter is, okay, if we're starting to understand and measure heights, let's say the height of this particular peak here. Do I measure from the reference ellipsoid? Or do I measure from the geoid? And this is something to keep in mind as you use different coordinate systems that use either a different reference ellipsoid or they use the geoid to base measurements from. Our next key term is how the map communicates between the locations on the map and those locations in reality, the real position on Earth. So what this is a model that describes the location, direction, and scale relationship with and between a fixed or known origin. So a datum essentially provides references to base a location on a coordinate system grid, so that's the horizontal datum, or height, usually from mean sea level or vertical. I just showed that previously. As I'll show, you can have local or regional datum or global datum. Here, once again, the reference ellipsoid is shown as a yellow line. This case, the purple line is the geoid, the Earth's bumpy, lumpy surface. And because Earth is elliptical and a geoid, not every reference ellipsoid is the same. When using a GPS to collect data, you'll want to make sure that the GPS data is using the same datum as wherever it will be displayed, like in ArcGIS or whatever mapping program you so choose. And the way we use the ellipsoid to fit the geoid is what we call a datum. And so here we use this particular reference ellipsoid for this particular area over here. Note that this surface over here, this reference ellipsoid matches up much better with it. And so this particular datum, this particular ellipsoid, is what we want to use for this particular local or regional area. However, the rest of the globe wouldn't want to necessarily use this particular datum. And so here the coordinate system is laid on top of this particular shape, and it's much more accurate because it's essentially a local or regional datum instead of a global one. There's really two common datum that you come across. You might come across a third, but if you are in research in a particular, let's say Europe, Asia, somewhere else in the world, you probably have access to data that's in a different datum than the ones I have shown here. So the NAD 27, when it came about, essentially recalculated the Latin long for 25,000 different control points. So essentially the Latin longs for various places changed. Then came the North American datum of 1983, and it uses the center of Earth's mass for the center of the ellipsoid, whereas the previous one, NAD 27, used an actual surface point there in Kansas to base the reference ellipsoid from. This one here, the NAD 83, used the center of Earth's mass to put that ellipsoid, the center of that particular ellipsoid. And since we're using a new ellipsoid, it caused a new recalculation of Latin longs across the country. So this is used in North America, not including Mexico, and it's going to be phased out. It's supposed to be phased out in 2022, but it looks like it's going to be phased out in 2024. So there will be something else that replaces this particular datum here in North America. The most commonly one used is what we see, the WGS84. This is the global system that also uses the center of Earth's mass for its ellipsoid. It's constantly being updated. So when you use a GPS, when you're plugging in data, more than likely you're going to be using WGS84. Even further, Google Maps, Esri, OpenStreetMap, Mapbox, Carto, they use this global datum overwhelmingly in their programs. And so all this, why I mention this, if you end up working a lot with computer map making, you will need to at least understand that having data in two different datums requires you to transform from one to the other to maintain the integrity of the locations on your map. Now, the thing is, these only tend to be just a 1 or a few meters off from each other. So when you overlay data and you see, this is just missing. There's this not overlapping. There's just a few meters off. Probably what's going on is you're in two different datum. And so you need to make sure that you're both in both of those particular layers are in the same datum. And then in other times, you'll get an error message that says unknown spatial reference. And so what that means is you have to then tell the GIS, hey, use this datum, this particular data, these points, this random table of X and Y coordinates. Here is where you want to lay those points using this particular datum. Finally, an unwritten rule is you tend to use local datums when mapping local areas. Now that we've established our datum, our reference ellipsoid that we will be using, we need to convert the reference ellipsoid to a flat map for our printer or for our screen. And so that's where we're going next.